This lesson covers how to make sketches of polynomial functions. We'll use four things to make our sketches: x-intercepts, y-intercepts, end behavior, and the behavior near roots. The first two you're already familiar with. The x-intercepts are also known as roots, and we have as our roots x equals 0, x equals 2, and x equals -3. So I'll plot those. The y-intercepts are when you plug in 0 for x and simplify the result. Plug in 0 for x, and we get 0 times -2 times 3, which is 0. We already knew that because we had a root at 0. The two new things that we're going to sketch start with the end behavior. If I were to multiply this out, I would get some sort of a third degree polynomial, x cubed plus x squared minus 6x. But to figure out what happens to this polynomial towards the ends, or in other words when x gets large, either in the positive or negative direction, the power function dominates the rest of the polynomial function. So as x gets huge, the squared term and the linear term don't really matter as much, and I think that my function is going to start to look like a positive x cubed graph. So to remind myself, I'm going to put a little arrow up here and a little arrow down here, because we know that a cubic function tends to go towards positive infinity as x gets large positive, and tends to go towards negative infinity as x gets large negative. The last step is to figure out the behavior near the roots. I'm going to take each root individually and plot what the behavior looks like. So I'm going to say when I'm at x equals 0, I'd like to know what the function does. Well, I don't want to plug 0 into the first term because that would produce 0, and I already know that 0 is a root. So if I leave that first term as an x, I'll plug in 0 at the other two terms. I find out that at x equals 0, I have something that looks like x times -2 times +3, which is -6x. So as I go near x equals 0, I'm going to have a linear shape with a negative slope. So to remind myself, I'm going to draw a straight line with a negative slope. I'll repeat that process at the other two roots. Near or at x equals 2, I'm going to plug into my function everywhere except where it would produce a 0. So I'm going to plug into the first space and the third space. I will have 2, x minus 2, and 2 plus 3. 2 plus 3 is 5, 5 times 2 is 10, so I've got 10 x minus 2, which simplifies into 10x minus 20. At x equals 2, I have again what looks like a straight line with a positive slope. So at x equals 2, I'm going to draw a straight line with a positive slope. And in the third root, x equals -3, at x equals -3. When I plug in everywhere except where it would give me a 0, I'll have -3, -3 minus 2, and x plus 3. -3 minus 2 is a -5. -5 times -3 is a +15. And near x equals -3, I have, again, a linear shape with a positive slope, 15x plus 45. So at -3, I have positive slope. So if I connect my two end behavior arrows with the behavior near these three roots, I can sketch a rough graph of what the polynomial looks like. It's going to travel through this root in a positive linear fashion. It's going to turn around at some point, come through this root in a negative linear fashion, turn around at some point and come up through that root in a positive linear fashion, and then going upwards in that direction. This is just a rough sketch. We won't be able to figure out where the local maximum or local minimum are. That's a calculus topic. But if I were to use a calculator or computer to look at the graph, the real graph, I can compare it. And see that while my maximums or minimums are way off, my behavior near the roots seems to be pretty good. It looks like I've got This root plotted in the right spot, and they both have positive slopes. This root plotted in the right spot with negative slopes, and this root plotted in the right spot with positive slopes. So my behavior near the roots is fine. I just don't know where the maximum and minimum are, but again, that's a calculus topic. So as a second example, I've got something very similar, but this time the last term is squared. So I'll go through the same steps. My x-intercepts or my roots are x equals 0, x equals 2, x equals negative 3. My y-intercept this time, I'm going to plug in 0 for x, and I get 0 times another two terms, which don't matter because I'm going to get 0 again. And for the new material, the end behavior. So let's plot my roots before I do the end behavior. I've got 0, 2, and negative 3. My end behavior, which I'll abbreviate as EB, this time if I were to multiply out the function, I would get x times x squared, or f of x is going to equal x to the fourth plus some other terms that don't matter. All I care about is that the polynomial is a fourth degree polynomial. Since all the coefficients are positive, my fourth degree polynomial is going to have the U-shaped graph. So at the ends I have both arrows pointing up because fourth degree polynomials have the U-shape. Fourth degree power functions have the U-shape. And so lastly, to find the behavior near the roots at x equals negative 3, moving from left to right, I'm going to plug in negative 3 everywhere except where it would produce a 0, negative 3, negative 3 minus 2, and I don't want to plug it into this last term because that would produce a 0, x plus 3 squared. Simplifying, negative 3 times negative 5 is a positive 15, and this time I have a positive 15 x plus 3 squared. X squared is a parabola, or a quadratic, so I know that I've got a positive quadratic, which is U-shaped, opening up. So at negative 3, I'm going to have a parabola-shaped root behavior. At x equals 0, again, when I plug into all the terms except those that would produce a 0, the first term is going to stay in x, the next term is 0 minus 2, and the last term is 0 plus 3 squared. Negative 2 times 9 is negative 18, negative 18x, linear shape with a negative slope, so through the root at x equals 0, negative slope, but linear. And then the last term at x equals 2, plug in everywhere except the term that would give me 0, 2, x minus 2, I'm not going to plug in there, and 2 plus 3 squared. 5 squared is 25, 25 times 2 is 50, I've got 50 x minus 2, 50x minus 100, again linear shape with a positive slope, so at 2, linear shape, positive slope. So again, connecting my end behavior prediction with the behavior near the roots, function's going to come down, bounce off the root at negative 3, come up, turn around, travel through 0, 0 in a linear shape, turn around again, travel through 2, 0, 0 in a linear shape, and then head upward so that both ends are facing upward. And again, using some sort of a graphing utility to find the answer, it looks like my end behaviors are okay, pointing up and up. It looks like my roots are okay. Here I've got a root that bounces. Here I've got a root that goes through 0, 0 in a negative linear fashion. And here I've got a root that goes through 2, 0 in a positive linear fashion. So my roots are okay, my end behavior is okay. The only thing I don't know is where the maximum and minimum are. But again, that's a calculus topic. The third example, the x term is being replaced by 1/4, but we're still going to use the same process. Now the roots are at x equals negative 2, and x equals positive 3, but the root at the origin disappears. The y-intercepts now, plug in 0 for x, and we get 1/4, 0 plus 2, 0 minus 3 cubed. 1/4 times 2 is 1/2. 3 cubed is negative 27. So we wind up with negative 13.5 as our y-intercept. That's way off our grid here, so it's just going to be somewhere way down there. And now to analyze the behavior near the end behaviors, multiplying this out, I would get something like 1/4 times x to the third, which is 1/4 x to the fourth. So as x gets huge, either in the positive or negative direction, I'm going to have a power function of 1/4 x to the fourth. Even powers look like U-shaped graphs, and the ends travel upward in both directions. Since the 1/4 is positive, I know that I'm going to have an upward shaping U at both ends. Now for the behavior near the roots. At x equals negative 2, plugging in everywhere except where I would get a 0, 1/4 x plus 2, negative 2 minus 3 cubed. Negative 5 cubed is negative 125. 1/4 of that is just negative 125 over 4. Multiplied by x gives me a linear result. Negative 125 over 4, x plus 2. I know that 125 quarters times x gives me a negative slope but a linear shape. So at negative 2, negative slope, linear shape. At x equals 3, plugging in everywhere except where I would get a 0, I have 1/4, 3 plus 2, and then x minus 3 cubed. 3 plus 2 is 5. 5 times 1/4 is 5/4. Multiplied by x minus 3 cubed. X cubed is going to look like a cubic function. Since 5/4 is positive, it's going to look like a positive cubic function. So it's going to come from below, hug the x-axis for a little while, travel through the root, hug the x-axis a little bit more, and then travel upward again. So connecting my two end behaviors with the behavior near my roots, I can sketch a graph. I know that the y-intercept is somewhere way down here, so I can finish the graph by traveling from up and to the left, down through this root in a negative manner, very far down, coming back up, traveling through the root in a cubic manner, and then off to the right. So checking what the real answer looks like, I have the behavior near the roots pretty well defined. I've got root of negative 2, negative slope, linear shape, a y-intercept way down here somewhere. I predicted at negative 13.5. Cubic behavior near this root, and then the end behaviors are up on both sides. So the last example involves going backwards, and your job here is to find some function from this graph. We're going to look at the exact same things we did in the previous graphs, but in the opposite order. My end behaviors, up on the left side and down on the right side, which means I'm expecting some sort of an odd power function, but with a negative in front of it, because it's up on the left side and down on the right side. My roots are negative 1 and positive 3. And my behavior near the roots looks like linear with the negative slope at the negative 1 and a bounce or a negative parabola at the positive 3. So when I start building my function, my y-intercept is also 0, negative 3. So when I start building my function, I'll start with the roots. F of x is some sort of a coefficient, x minus the first root, negative 1, times x minus the second root, positive 3. I need the behavior near the first root to be linear, so I'm okay with that exponent being 1, and the behavior near the second root to being parabola, raising to an even power. To find out the a term, I'm going to use x and y plugged into my function and solve for a. Negative 3 equals a, 0 plus 1, 0 minus 3 squared. Simplifying, negative 3 equals a, 1 times negative 3 squared is 9. And I wind up with a equaling negative 3/9, which is negative 1/3. So it looks like I took care of everything. My final answer is f of x equals negative 1/3 x plus 1 to the first x minus 3 squared. My degree, first degree, the squared gives me a total degree of 3. Negative cubic does have end behavior that looks like this. My roots are at negative 1 and positive 3. And if I were to test the y-intercept, I would wind up with a y-intercept of negative 3. So this is one version of an acceptable answer. There's other versions allowed because I don't know whether this root here would have a second degree or fourth degree or sixth degree. So any even power here would be acceptable. This term here has to have 1 as its exponent because that's not cubic at the root of negative 1. It looks linear, so that has to be not any odd degree, but it has to be a first degree.